We're going to talk about the relative boiling points of different compounds. And we do this in this chapter to talk about a trend with alkanes that is similar to that of heat of combustion, but for a different reason. So we're doing it partly so that we make sure, even when we have two trends that follow the same pattern, that we can tell the right story with the right, or give the right explanation for the right pattern. It's also a great chance for us to review intramolecular attractions, which is why basically why molecules stick to each other. Now, if you imagine all the molecules in this beaker, that a poorly drawn beaker of boiling liquid. Okay, so it really doesn't look any better if I make it bigger. But imagine that inside the beaker there's water molecules, right? And we'll just kind of draw them as little blobs. And they're all kind of stuck together, right? In order to get them to enter the gas phase, or go from a liquid to a gas, you have to apply enough energy to overcome the attraction that they have for each other. Like, they like to stick together. In a liquid, they're all touching each other. In a gas, they're all flying around independent of one another. So you have to apply enough energy or enough heat to break up that attraction. Now see if you can remember, what are the intermolecular attractive forces? Yes, we've got ion-ion attraction, or ionic bonding. That's actually the strongest one, right? That's a positive and a negative that are attracted to each other. There's the hydrogen bonding, which is a really important one, and we never have too many excuses to talk about this, right? This is what happens in water. Water is a very polar molecule. There's a big partial minus on the oxygens and a big partial plus on the hydrogens because of the large difference in electronegativity. And we say that hydrogen is the attraction between the partial plus on the hydrogen and the partial minus on the oxygen. Now, this is essentially a specialized dipole-dipole attraction. So what is a dipole-dipole attraction? Well, it's hydrogen bonding on something that doesn't have a highly electronegative element, like a nitrogen, an oxygen, or a fluorine, and a hydrogen. Last, we have London Dispersion Forces, and this is essentially our catch-all for why non-polar stuff sticks together. Non-polar stuff, for example, alkanes and other hydrocarbons. So if you have a molecule like butane, or we'll just draw an even easier one to draw, like propane, that's all carbons and hydrogens, all non-polar bonds, the attraction between one propane, and let's just draw as if, oh, here's the surface of the molecule, right? So we'll just draw propane like it's a little squiggly, and here's another propane. The attraction between two propanes, which we call either London Dispersion Forces or the induced-dipole effect, is a fairly weak attraction, at least on an atom-per-atom basis. Now, gasoline's a liquid. It's made of hydrocarbons with chains typically between maybe 5 and maybe 10, 12, or 15 carbons. Wax is a solid, and it's long chain hydrocarbons, maybe 20, 25 carbons long. And so this attraction, this London dispersion force, as those molecules get bigger and longer, the attraction force adds up, right? This weak attraction between the molecules. It's like a piece of molecular Velcro. The larger the surface area, the higher the attraction. The higher the attraction, the more energy it takes to separate those molecules, and the hotter you have to get it before it boils, right? So therefore a higher boiling point. Now, if we consider isomers, let's say like butane again versus isobutane. Butane, the less branched isomer, it has a larger surface area with which to overlap other butanes than an isobutane does. So, bigger overlap in the non-branched or unbranched isomer. Means that it has more attractive forces and a higher boiling point. Now note that this is kind of like, when we think about this and comparing to heat of combustion, is like ice cream and shark attacks. Right? We eat more ice cream in the summer, we're more likely to be attacked by sharks in the summer. This does not mean that eating ice cream will cause you to be attacked by a shark. It just simply means that both of those things depend on a common factor, namely the fact that it's hotter outside in the summer. And so the surface area, or the size of the molecule, the shape, or rather whether the degree to which the molecule is branched, is the common factor or variable in both boiling point and heat of combustion. But the two are unrelated. Boiling point, and let's make note of that here, boiling point is about intermolecular attraction, molecules sticking to each other, whereas the heat of combustion is about intra or within molecules, or intramolecular forces. In particular, we could think of it like bond strengths. It's actually a little more complicated than that, but it's definitely a rabbit hole we don't want to dive down right now. Point here is that we have a trend with boiling point. We want to know it, and it's a great opportunity for us to go back and review the other intramolecular attracting forces, because here we're looking at hydrocarbons, right? So butane versus isobutane. If we put an alcohol group on there and gave it the ability to hydrogen bond, the boiling point would be way higher.